This is an overview of the p-value of regressions. This is a way to test if the regression model fits the data or not. What's really happening is we're testing the null hypothesis that all of the regression coefficients are zero. In other words, the regression doesn't fit the data at all. A smaller p-value means it's less likely that the null hypothesis is true. We want small p-values. Figuring out the p-value of the regression involves the F statistic and the entire F probability distribution. The first major step is calculating the F statistic. To do that, we need the sum of the squared error, and the difference that's being squared is between each data point and each model point, each regression model point. And then the regression sum of squares, RSS. To do that, the difference is between each regression model point and the mean value of the data, and then that's squared and then summed up. We also need the polynomial order, PO. It equals 1 for linear regression. The residual degrees of freedom, nu equals n minus 1 minus PO, where n is the total number of data points, and the mean square error, MSE, which is the sum of the square error divided by the residual degrees of freedom. That's SSE divided by nu. The F statistic can be calculated as the regression sum of squares divided by the polynomial order divided by the mean square error, or F equals RSS divided by PO divided by MSE. F is proportional to the ratio of the variances of the model and the residual. This ratio is larger for a better fit. The next major step is looking at the F cumulative distribution function, and that's what's plotted here. It's sometimes called the FCDF. For that, we're looking at different values of F, not just the F statistic, and that's what's on the horizontal axis. And the F cumulative distribution function ranges from 0 to 1. The 0 to 1 reflects a probability range, and that's what's on the vertical axis. The F cumulative distribution function depends on three parameters. One, the F value chosen, that's along that horizontal axis. And then the other two parameters are types of degrees of freedom associated with the probability density function. The first one for regression is PO, the polynomial order. And the second one is nu, the residual degrees of freedom. The next step is calculating the p-value of the F statistic, the p-val. Sometimes that's written as FP-vals as a function of F, the F statistic, PO, and nu. On the graph, the F statistic is marked off on the horizontal axis. And then if we go up from there, there's a dot on the F cumulative distribution function that corresponds to the F statistic. Going over to the vertical axis, that value of the F cumulative distribution function is 1 minus p-val. In this graph, 1 minus p-val is really close to 1, which means that p-val is very small. The final step is setting a threshold for rejecting the null hypothesis. And remember that null hypothesis is that all the regression coefficients are 0. The threshold value is alpha, and it's often set to 0.05, corresponding to 5%. The 1 minus alpha line is shown on the graph. If the 1 minus p-val level is above that, it means that p-val is less than or equal to alpha. If that's the case, then we can reject the null hypothesis. If alpha is 0.05, in that case, we can say that the model has some value at a 95% confidence level. The p-values are often reported. For instance, if the p-value were 0.01, it means that the null hypothesis is rejected at a 99% confidence level. It's important to remember that, in simple terms, rejecting the null hypothesis means that the regression model is better than nothing. That's important to check, but it's not a very high bar to get over. It's important to use additional statistics to characterize how well the regression model works. For instance, the root mean square error, or the squared correlation coefficient, or the adjusted squared correlation coefficient. Nevertheless, the p-value of regressions comes up a lot, and it's important to know how to calculate it and to interpret those values.